All right, thanks everyone for coming out again. Today we're going to continue our discussion on rank structures matrices. In particular, we're going to talk about how using the class of rank structured matrices HSS, or hierarchically semi-separable matrices, which we talked about last week, we can get linear time solvers. So to start out, I'm going to review the HSS structures. I know the form can be a little complicated when you first see it. So we'll again look at the tree structure, the block structure, and talk about how we basically traverse the tree to get basic ideas out of the matrix. Then the heart of the lecture today will be the techniques we use to solve these matrices very quickly. In particular, nested dissection and structured Schur complements, which on their own are not algorithms. But they're very, very useful tools you may or may not have seen in a class like CS 515. So I'm going to go over them in some detail, because these are the two primary tools we're going to use to make sure we get linear complexity. I'll kind of show some examples of the types of matrices we use these kind of tools on. In particular, these will be coming from a lot of elliptic PDE problems, are what I'm very familiar with. I think a lot of you may be too. Then finally, we'll briefly at the end go over the HSS ULV algorithm itself. There's a lot of subtleties to it, but I hope to go over the very important steps, which I think will give you a good idea of how it works, why it's different than just a general LU or GMRes, and why we're able to get this linear time that we may not have for another method. Okay. So back to hierarchically semi-separable matrices. The key here is we start with a post-ordered binary tree T, which will have root tk minus 1 at level 0. And we have a set of HSS generators. And each set of generators you think of is an array of small matrices. Matrices on the order R by R, where R is log n or smaller. And with these matrices we have du, v, r, w, and b. And they satisfy these relations, where di you can think about as all the off-diagonal blocks of the matrix. And in particular, you can generate them recursively using the U and V matrices, which are the row bases at different levels. And this is the formula that does that recursively. And then moreover, you can generate these row bases hierarchically as you go up the tree using R's and W's, which I will give a much better representation of pictorially on the next slide, which show kind of the relationship as we go up and down the tree.
You said the DI represent off-diagonal blocks?
Represent diagonal blocks. Okay. If I said off-diagonal, I apologize. That would have been a very, very bad typo. DI or diagonal, everything else represents the off-diagonal row bases and how they relate to one another. Thank you very much, Kyle. OK, so this is what it looks like when you actually have it converted into HSS form. You have the D's in the diagonal. And this is I took a picture of the symmetric case because it's less clunky. With non-symmetric, I'd have to write twice as many letters and everything. It just would be, it's not as clean of a picture. But what I like to show from this is our binary tree. And we see we have the D's we list at the very bottom and the U's at the very bottom, because we only explicitly calculate the row bases and the column bases at the very leaf level. Everything else is just done hierarchically. And you think of the R's and the W's are as we go up and down the tree. And the B's you always think of as whenever you're crossing over from thinking about what row you're at to what column you're at. That's where the B comes into play. So I really like this picture. It kind of illustrates kind of how we generate this. And I'll go through a more concrete example of this, how we would find a single element in just a slide. But does this picture make sense, kind of showing what the generators are doing?
So because it's symmetric, so you said R and W is equal. Is that what it is?
Yeah, that is what we did. In the symmetric case, R and W are equal, and U and V are equal. And that's very simply because the row bases and the column bases are identical for a symmetric matrix.
So non-symmetric, so each edge will be R and W, or just the left edge is R and the right edge is W?
There will be so that's why I drew the symmetric case, because in a non-symmetric case, the edges are both an R and a W.
So each edge will be R and W?
Yeah. Yeah, and the R represents as you're going up the tree, and the W's as you're going down the tree. So
basically, this tree edges are two directions.
Yes, they are two directions, yep.
Go up, R, go down, W.
Exactly, exactly. And again, I just reiterate some features why we like HSS matrices. They were invented to be parallelized, so that can give us some very fast algorithms in practice. The storage is only linear, as long as you do use randomized sampling techniques. And we can write the matrices all in terms of rank on updates, which is a very well-developed theory historically in numerical linear algebra. And then the obvious one, we have very fast operations for basic linear algebra subroutines. Yes?
So if I just wanted to do, say, a dot product of an input vector and, say, a row that corresponds to an entry that is in block D1.
Okay.
So the whole row, a row of the whole matrix, I want to dot product with an input vector. I'm just trying to understand how I would use the tree for this.
For something in D1?
For a row that is contained in D1.
So in D1, you would be using standard linear algebra techniques. I should stress, for the diagonal blocks,
right,
we're dense, we're keeping them as dense.
I understand that, but the rest of the columns to the right of block D.
Oh, so you want the entire row?
Yeah, the whole row, but just for one of the rows that happens to be contained where the D1 block is.
Okay.
So yeah, so how do I use the tree to access?
So the tree gives us a very nice. Yeah, I'll skip ahead for a second.
Sorry.
Yeah, no, I'm going to answer that question, I think. So yeah, everyone, so I would love to answer Kyle's question. I think that really springboards into what I'd like to talk to next. But everyone gets the basic idea. Again, I'd like to, before I answer Kyle's question, I'd like to emphasize the idea of an HSS block row, which is that any of the different colors here and the off-diagonal blocks all have to have rank. In some literature, you see it as K and some as R, but some number or smaller. And this particular, because you have the block rows, this is what allows for hierarchical construction. I really want to stress this. Without this, it is not HSS matrix. And then this is just a picture that kind of illustrates how we do construction, which I won't say too much on today, but I'd like to emphasize the concept that we only explicitly get the row basis and column basis at the very leaf level, and everything else is just built up hierarchically. So now I'm going to answer Kyle's question. And this is a slightly simpler question, but it's the exact same idea. Let's say we have a 400 by 400 matrix, and we only want to access a single entry. And I can analogously, as I talk through this slide, extend that to a row or a column or anything. Now, we would never want to form an entire HSS matrix explicitly, because that is n squared data. We lose all our efficiency. But very often, there's applications where you do want an entire row, entire column, or a subset of entries. And this we can do very, very cheaply. In particular, what the tree helps us do, there's very nice machinery to generate little m by m blocks at will very quickly. So if we look here, any of these 16 blocks can be generated very quickly in sublinear time using a very simple routine that goes up and down the tree. And if we only want a row of it, or a single entry, we modify the procedure, which I will show in just a second, taking only part of the submatrix, the generators up and down the tree. So let's take our example where we want only entry A200-201. So we want just the entry kind of right near the middle. And then I will extend that to if we want, let's say, the 200th row. Oh, and I want to emphasize here when I say m is just the size of the blocks. It can be really any small constant will work, but it has been proven by a number of people that the optimal way to set this block size is twice the HSS rank. And so that's what you will see in almost all of the software packages nowadays.
The HSS block size means the smallest, the smallest diagonal block size?
Yes.
The leaf, no,
the size of the leaf blocks.
Oh, the leaf, okay.
And they don't, and all the slides I'll show you today will show even what's called a regular grid, where all the blocks and box are the same size. That simplifies the analysis. I think it's a cleaner presentation. In practice, you don't have to do that. You can have varying sizes if your rank is not necessarily contained. It makes the coding a little harder, but the theory is really the same. Okay, so our example, I'm just going to show a tree with 4 levels, 0, 1, 2, and 3. And I emphasize here that it is a post-ordered binary tree. Unlike in the H matrix, you generally see them order from the top. Here we order in the order we're going to touch the blocks. So you number 1, 2, and then once all of a parent's children or a leaf's descendants have all been named, then you name the node itself. So 1, 2, then 3. Then you go back down the leaf, and 4, 5, 6. And now we see that all of 7's descendants have been named. We go up to 7 because when we do real algorithms, this is the order we process them in.
So could you remind me, so 1, 4, 8, 11 are associated with the diagonals?
1, 2, 4, 5, 8, 9, 11, and 12 are all associated with the diagonal. Everything on the leaf level.
The 8 one.
Yeah, all 8 at the bottom. Now there is, I like that you pointed out the left nodes because in terms of the coding and in terms of certain stability properties, there is a difference between the left nodes and the right nodes at any given point. So we do need to keep track of that. But all the ones in this bottom correspond to the diagonal. So that's a great question. Okay, so turning back to finding this 200, 201 entry. The naive way to think about it is forming the entire 50 by 50 block, I have 1 to 200, 201 to 250, and then just taking the entry we want. That's not how we would do it in practice. But I think that's the simplest way to first think about it. Because what we would do is we would just see, OK, we want to start where the row we're on is 5 in terms of our coordinates, rows and vectors. We're the 5th. So then that we use U5 and R5. Now we go up a level to now the blocks that are 100 by 100 and find the block that corresponds to us. Here that's R6. So we multiply by R6, and now we go across to the other side. And here, because we are again on the top half of the matrix, we use B7 instead of B14. We've now crossed over the tree. You always cross at the second to highest level. Never you don't actually have generators at the very top level. That just kind of indicates the whole matrix. So you always cross at the second to top level. So we have B7, and then we go down the tree, and we see that now we're at coordinate 201 for the columns. And so at the level it's 10. So we do W10 transpose, and then go down one more level, and 201 is in the 5th of the 8 boxes, and that gives us W8 transpose, and finally V8 transpose. So that gives us the entire 50 by 50 block. Now, if we only want a single entry, we just take individual rows out of U and V, which really condenses the size of those matrices. It brings the complexity way down. If you wanted an entire row, you would you would keep all U5, but you would only take a row out of V8. And for column, reverse it. So so for Kyle's question, if we wanted an entire row going across, what we would do, it's a great question. Really illustrates and brings together everything we're doing. So for the D1 part of the row, we just do it by brute force. For the 1, 2 block, we would get the bottom row of that block by doing the whole construction, but only taking one row out of V in that sense. And then for the final half, we would again construct that whole, not the whole submatrix, but a row of it by only taking, again, one row out of the appropriate V matrix. So you'd have to do it for each block. And in reality, you wouldn't just have 3 levels. You would have maybe 15 or 16. But again, each component of that would be sublinear. So even though you'd be doing log n many of them, even generating an entire row is still a linear operation, which is very feasible, and that's why we do it a lot in applications. Kyle, does that answer your question? Great. OK, so and just to kind of summarize the expense of just generating an entry, we see that all these matrix products are they're really just matrix vector products for a single entry. If we want to generate a row, they would still be matrix, they'd be matrix, but still very small. And we get the whole thing is on the order of log n to some power. And this is something we are very familiar with in HSS operations. What you will see from inversion to matvex to eigenvalues, basically every HSS operation that has a mature algorithm, the operations will scale both in time and storage as n log alpha n, where alpha is either 0, 1, 2, or 3. I think the best operations we have are for matvex. It's just like And for eigenvalues, and if you want both the eigenvalues and the eigenvector, I think is where that alpha is a 3. Usually it's a 1 or a 2.
Could I ask how big could be the constant in the big O notation?
Yeah, the constants tend to be on the order around 600–700 in a lot of algorithms. So there's a crossing over point. These are not useful for small matrices. But if you're talking matrices, once you get to higher than 10,000, especially closer to 100,000, they start to destroy normal cubic solvers.
You said 10 to 100,000 somewhere in there?
Yeah, it depends on the algorithm. Usually by 10,000 you're already be better. By near 100,000 it's not even close. Okay, so now I'm going to talk about nested dissection for a while because this is, I said, one of the main components of HSS solvers. And so to really give it the proper treatment, we're going to have a model problem that's going to come from PDEs that we're going to use as we describe it. So in particular, this is just take any elliptic operator. So you can think of Laplace, Helmholtz, convection, diffusion. The reason I'm taking elliptic is because all discretizations of elliptic operators are HSS. So these are the ones we would actually see in applications, which is great. So this is standards from PDEs. We do discretization. In particular, let's do something simple. Let's just take a 5-point stencil, because this isn't a PDE talk. You can do other things. You still get similar properties with your matrix. So for instance, for the Poisson equation, this is what we would get. And just to give some examples, this could also work. I'm going to show to kind of have matrices with differing rank properties. A little later, I'll also do this on a grid conduction problem. And basically, you can do this on any elliptic PDE of this form. And you will get your discretization will have HSS properties. OK, so nested dissection is, I like to think of it as just LU with a really smart choice of pivots. In a first numerical linear algebra course, or even a linear algebra course, you talk about systems. You learn Gaussian elimination, and then you learn how to pivot to help stability. Then when you learn more, and you get into sparse matrices, you get really concerned on when I'm forming my Schur complements, how do I avoid fill-in? Because if I get lots of fill-in, everything we've worked for with our sparsity is gone. And nested dissection for large class of matrices is really the way to go about this, to do the pivots in just the right way where you, in a very precise sense, minimize your fill-in. And I'll talk about how we do that and why it works so well. And it is a very brute force. I call it brute force LU. But as I show here, even without rank structure, for the next 10 minutes I'm going to do nested dissection with no rank structure. We can still get, for these elliptic PDE problems, n log n or n to the 4/3 power even for a 3D problem, which is very good. And we can do analysis on them because they're direct methods. We know exactly when it's stable, when it will when it'll work. We don't have to worry about convergence because it's direct. There are also iterative methods that work very well for large classes of sparse matrices. You're probably familiar with many of these, like GMRes. And these involve lots and lots of matrix vector products. And in a lot of cases, they are the fastest way to solve linear systems. The issue with these is it is very, very difficult in general, or even for specific cases, to prove how fast and when they are going to converge, which doesn't always make them ideal to use. Multigrid, created by Wolfgang Hackbusch, I mentioned last week, is very similar to an iterative, well, it's a type of iterative method. Really the only idea that makes this different is you kind of nest your grids hierarchically, which brings us right to H matrices. Again, this is hard to do analysis on and only works better for some problems than others. We want more of a black box algorithm that's still going to be very fast. I'll mention one more, FFT, which only works for a very small subset of problems. In terms of PDEs, it would be when you have, I think, the constant coefficient case. I think you might even need smooth geometry as well. And in those cases, it's super fast, but it only works for a small subset. So we're going to focus on brute force, but with nested dissection, and then later, how we can accelerate it for the case where the matrix is HSS. OK, so nested dissection, again, I say how to choose the pivots. This is first attributed to George in 1973. And the idea here is we want to break up our matrix in such a way that the interactions between all the submatrices are only very local. elements only talk to the elements very close to it. And that will ensure that we don't have a lot of fill. And in particular, when we form our Schur complement will also be sparse. So this is a lot better with pictures. So here's a very simple example. This is one level of dissection. And we divide our domain into 3 pieces, where we have 2 pieces that are basically half the matrix and one what we refer to as a separator. And what this ensures is the non-zero blocks of the coefficient matrix will have this sparsity pattern, which isn't, it doesn't seem that much sparser, but what's great about this is when we think about inverting it. Because if we were to just, by brute force, think about what the inversion would be, it would be from this formula, basically just the concept of forming the Schur complement. And what we get really excited about is this allows us to do the inversion by inverting A11 separately and A22 separately. And this screams recursion. Yes, we found a way we can just break it up, do some sort of divide and conquer, and do smaller and smaller and smaller and smaller subproblems. So this is a very exciting idea. So yeah, we already see that the Schur complement computations are getting smaller and smaller because we can do smaller inversions, which is the most expensive part. Now, I said inversion because it's a simple way to first present it, but you guys know we would never do inversions in practice. And that's because they tend to be slow and they are never very stable. So the way we actually do this is we do the analogous computations with an LU decomposition. So again, this is really the same thing. And the whole key here is when we compute an LU decomposition of the big matrix, we can do LU of A11 and LU of A22 individually. And then we can combine them. So we want to do more levels than just one because we want to gain lots from this. So to kind of show what this looks like pictorially, this is our matrix with one level, one separator. Then you always alternate vertical and horizontal. And you do 2 to the power n separators each 2 levels. So this is 2 levels. So here we notice that this off-diagonal block doesn't talk to either of the other 3. So already we've saved lots of computations. We can do all the inverses explicitly. We keep going and going and going. And this is, you would go a lot further in practice, but this kind of shows you now we've divided it into lots of subproblems where we can do all the LUs independently. Now, I kept talking about Schur complement, and I want to illustrate this with a visual because this is where we really get into trouble if we don't do nested dissection. So this is the sparsity pattern of the operator I showed you in the model problem if you don't do nested dissection. And we can already see if we were to just do LU on the first column, all the fill-in it would create right away. Where with a nested dissection, we get something more like this. A so-called arrow matrix. And this we already see just completely alleviates us from that problem. It allows us to do very, very small LU decompositions. And because that's a cubic operation, we don't mind having to do a lot of them.
Jimmy, before you, what are the red lines delineated here? Those are the small blocks that we just saw in the grid in the mesh, right?
Those are the separators.
Okay. Yeah.
Yep.
So separators meaning after the work is done, the blocks that we actually do LU on are contained inside the red lines, right?
Yes.
Okay, cool.
Yep. Okay. Is everything so far clear? Great. Great. Okay, so how much did we save in terms of doing this, doing this nested dissection? So we have to think, this is a hierarchical operation, so we have to think about it level by level. So at the top level, the divider has n squared points. And we need to perform dense inversion on the very small matrices. So we have to cube this n square root terms, and we get n to the 2/3. Now we go down to a level where we have 2 dividers, and we see that we need to, again, perform our dense inversions on the separator, and we get the cost of processing is 1/2 n to the 2/3. And we repeat this process, and we see that the total cost for this whole thing, if we have a 2D problem, is n to the 3/2 or for a 3D problem would be n squared. So this is great. I mean, this is better than, you know, it's better than the n cubed of just normal Gaussian elimination, but it is still not, I mean, linear time, linear complexity is really the gold standard for modern day computing. So we still are not totally satisfied with this kind of thing. But is it clear, you know, why it is as fast as it is? For this is still a general sparse matrix. Okay. So again, to summarize, these are the costs. And there are a lot of good software out there that already does this, both in Fortran, C++. There's a lot of really good libraries. And I would, you know, highly recommend these kinds of codes. They've been around for a while. So if you have kind of moderately sized problems, sparse problems with no rank structure, you know, this is the way to go. It's when you get into really, really big problems, higher dimensions, more complicated stencils, when you really need to consider the rank structure. Because like we talked about, the constants in HSS algorithms are in the order of hundreds, where these algorithms, basic nested dissection has a lot smaller constants. But we do want to improve the complexity. And the key here is that these Schur complements, which I'm going to define explicitly here, you know, if we see if this is, again, we go to a very simple 3-domain problem. This is a Schur complement. In the case of an HS matrix, the Schur complement is also rank structured, which is something I will not prove explicitly, but it's in a lot of papers, a lot of good work's been done on it. So that's great. That means all the intermediate algebra, when we do our nested dissection, when we do our LU, is fast. Is not cubic anymore, which is great. So if we recall our initial problem, I think I first started with a Laplace, you know, the very basic equation. We get off-diagonal ranks like this for a 400 by 400 matrix. Clearly, HSS. This graphic doesn't test all the HSS block rows, but take my word for it, the block rows are also all off-diagonal. The whole rank of this HSS matrix, I believe, 9. So that's, you know, for a 400 by 400 matrix, that's very good. Clearly a lot less than log n.
What's the number 6 and 7?
So these show, if you do, to generate this graphic, I just did an SVD. I didn't do anything fancy on each of the blocks. And these are the numerical ranks to a tolerance of 10 to the negative 6th.
So the first level off is 7, and you go down, becomes 6. It's even smaller than
yeah, and this you'll see this pattern a lot. In general, you know, and if you want to be rigorous, you have to test all the off-diagonal blocks. But 9 times out of 10, well, depending on the application, but a lot of times, the furthest block, that's where your largest number is going to be. So if you just want to estimate it, you can get a very good lower bound by just doing the rank on that off-diagonal block. So this is great. This is really good for us. Oh, so this is, I'd like to mention, this is with tolerance, I think that's a typo. It should be 10 to the negative 6. Yeah.
So this whole matrix is the Schur complement matrix, not the original input matrix. I just want to be clear. This matrix, when we show 6 and 7 and it's off diagonal blocks, this is the Schur complement.
No, this is our original matrix.
Okay.
And I'm showing the Schur complement has the same properties. But I wanted to clarify that the matrix we're working with is HSS.
This is the original
yes.
input model problem with coefficient matrix,
yes.
which is HSS.
I apologize if that wasn't unclear. And then I'm going to show that the Schur complement will also be HSS. Yeah, I'm sorry, I should have clarified that. Thank you. Just one point I'd like to emphasize, if we, I guess, crank down the tolerance, we get ranks a little bit higher. Let's say we wanted accuracy to the negative 10, we get a little higher blocks. So in practice, you know, we talk about that constant. When you use HSS solver packages or HSS eigenvalue packages, you can specify a tolerance, how many digits of accuracy you want. And that will have a big effect on, usually only on, you know, the order of, you know, linearly with the HSS rank and the tolerance you want. But going in general from like 10 to the 6 digits accuracy to 10, 11 digits accuracy, that will double your computational time, which makes sense. Okay, and again, this just graphs the singular values. And again, for our just basic 5-point stencil problem, we see they decay very quickly. And even though none of them are non-zero, so it'll be a totally dense matrix, you know, they're basically adding nothing past the first, you know, first dozen. Okay, So, and again, if we have something like a grid conduction problem, we do the same thing. And this is a little higher. I told you I want to show you varying. But again, even to high accuracy. And again, we see the furthest off-diagonal block is the one with the highest HSS rank. We get 21. So this is still very good for the size of the matrix. And we see again that our singular values decay in the way that we like them. I'll give, I think, one more example. This is where the aspect ratio is cranked up. And again, we get this. OK, that's enough examples. Oh, Helmholtz. I would like to mention this problem. So something you have to look at for HSS, this comes up a lot in applications. Your frequency, the underlying frequency in PD problems actually does play a very big difference. There have yet to been, yeah, this is worth mentioning, yet to been a lot of work done for high frequency problems. In that case, a lot of times the HSS structure does corrode and is not quite there. So this is a Helmholtz problem with low frequency. And we get very nice, and this would be the solution, we get very nice HSS rank. But if we do a more high frequency one, this is no longer useful to us. We see it's almost full rank on the off diagonal. Not quite, but larger than log n, which means it will no longer be linear complexity. So that's something you have to watch out for in practice, is the frequency of the underlying problem. So this would not be suitable to HSS ULV. OK.
So I have a question. So basically you demonstrate that the Schur component preserves the HSS ranks.
Yeah.
So is there any proof, I mean, the HSS rank of the original matrix and the HSS rank of the Schur component?
Yes, yes.
Upbound the, is the input upbound the HSS rank of the
yes.
Schur?
Yeah, and it'll in practice be a lot smaller, especially for some of the really small blocks. But you can, and that has been proven. I know Jha and Chandrasekaran have a paper on that. Mingu did some pioneering work on that. Yeah, that is, you're absolutely right. That is the upper bound.
Bounded by the input.
Exactly. Yep. So, and I'm going to not omit the proof here, partially because it's long and tedious, and partially because I'm not sure if I totally understand it. But it has been very rigorously proven that that is the case. So, in particular, we got to think about how much this costs and how cheap does our algebra of the Schur complement need to be to really drastically reduce the costs. So, suppose the cost for inverting these Schur complements, which are in HSS form, is m to the alpha. So in the non-HSS case, alpha is 3. Ideally, we like it to be, especially with randomized sampling techniques, we can really get it to 1 or very close to 1. And we see here, the break-even point to get linear complexity for the whole algorithm, if we can do the algebra of the Schur complements anything less than quadratic with an SI section, we're set. So even before randomized sampling came into vogue, this was already being used. This idea of you do HSS operations, you can bring the whole linear solve down to n log n. Even for a cubic problem, we see that if we can get the alpha less than 3/2, we still have linear complexity for the whole algorithm. And this is just doing very basic complexity analysis. So yeah. Oh, no questions? OK. Good, good. Yeah, and so with randomized sampling, all the technique, the factorization, the solution, and the construction can all be done in ON. The construction I have not talked so much about, but now I'll talk about, now that we know the ideas that our Schur complements are going to be structured, and we know about the nested dissection, I'll give the algorithm of how we, step by step, how we do this for an HSS matrix. This isn't the most complicated HSS algorithm. I believe the whole thing in MATLAB can be implemented, even with all the tree subroutines, in about 500 lines. Obviously in Fortran and C it's a little worse. But and it's really only about, the basic idea is really only about 10 steps. So while I will not be filling in all the details, I really hope the next 6-7 slides really give you the flavor of how we're doing the HSS ULV. Please stop me at any time. This is supposed to be very high level, so let me know if anything is all unclear. OK, so we go to our HSS tree. And we go leaf after, OK. I want to introduce one more concept. And that is the idea, you see a lot here in the next few slides, you'll have things with the subscript S. S stands for switching. So there is in HSS algorithms a concept that comes up all the time called switching levels, where at some point on the tree we draw a line, where we have beforehand shown numerically or proven rigorously that anything below that on the tree, it's going to be faster for us just to use dense matrices, to not worry about the generators. And anything above it, we're dealing with big enough matrices where we want to do everything in terms of structured matrix computations. So on all of the steps of the algorithm, you'll see these if-else statements, where if you're above the switching level or below the switching level, do this. I think that's the only really confusing part about this. Now I'll go through it step by step, but does the idea of a switching level make sense?
So is this also the way that is implemented?
Yes.
So you're doing classical, so I mean you are only working on SPD matrix?
OK, this is the example for a Cholesky because it's cleaner. An analogous algorithm for non-symmetric works just as well. It would just take twice as long to show the full algorithm. But no, it does not have to be symmetric by any means. And when I talk next week about the eigenvalue problems, it does matter if it's symmetric. There's a lot of things I can say about the symmetric HS eigenvalue problem that I have not been able to prove about the non-symmetric. But for linear solvers, symmetry doesn't matter. Sparsity doesn't matter. We can handle anything that's in HSS form. OK, so we go to each of our leaves. And at the when I say leaf, at the very bottom level of the tree, we compute dense Cholesky factorization. So that's a cubic operation, but it's stable. We know we do it accurately, and because it's at the very bottom matrices, it's not an overall expense. And we initialize for each leaf what we call this F matrix Fi. And I'm trying to see how I said this. OK. Then we compute this for Cholesky LLT as we're going across the levels. So here, this is where we're below the level. So everything is dense. And so our UI matrix is going to be here. We just get the Schur complement through very dense computations. And we see what we're doing as we go across the tree. OK. So that's what we do at the lower levels. It's just dense linear algebra. Does this make sense so far? OK.
F and I is the off-diagonal blocks, right?
Yes. Yeah, and I refers to the node we're at. Exactly. OK. Now, if we are above the switching level in the tree, what we do is we compute an HSX approximation to our Schur complement. And then we do a ULV HSS factorization of the Schur complement. So what that means is it's the same idea as a ULV as a general LU factorization. We have to add in a third matrix for stability because of all the HSS generators. But basically, we just build it up one at a time from each of the low components up higher. And then the only thing that we're doing dense is at with the U generators, with the very row bases and column bases at the very bottom of the tree. That's dense linear algebra. But everything else at the top level of switching level is done in terms of just very small matrices, small matrix vector products. And that's really the fundamental idea for the first part of the. So at this point, we're not solving anything. We're just doing a factorization. We do a ULV, so it's three matrices. Getting this structured matrix into a form where it's very easy to do a fast solve on it. And like I said, we do different strategies at the lower levels and the higher levels. So to kind of summarize what we've done so far, and then I'll pause for questions, we've factorized the matrix at different nodes, and we've done exact factorizations before the switching level. And after the switching level, we first do HSS approximations to all the Schur complements, and then do structured factorizations. So now we don't have our ULV factorization yet, but at individual nodes, we factorized all the Schur complements. Is that clear so far? OK. And the final step of the factorization is what's called extend add. If you're familiar with that from multifrontal methods, it's the exact same. But in case not all you are, I'll go over what I mean by that. So this comes up a lot in lots of theoretical computer science, the idea of pushing and popping stacks. So this is one of the places where we do think about if it's a left node versus a right node. This makes a big difference in terms of the algorithm. So if I is a left node, so any You have 1, 4, 10, 13, any of those on the left, or at any level of the tree, anything that's the left of its two children. What we do is we push UI, its row basis, onto the update matrix stack. Now conversely, if it is a right node, we pop uj. So for j all the way to the sibling. And the sibling is just the analogous node, the left if it's right, the right if it's left, that has the same parent. And yeah, and we just compute this for all the parents. I should have explained that. I wish I could have written that a little more clearly. I apologize. But this is, I mean, if you are, I think the literature for multifrontal methods explains this a lot better than what I just did, if you have any more further questions. But basically, you do that all the way up the tree. And what you wind up with, I like this graphic. It shows kind of, I should have done intermediary stages. But it shows how the HS tree transforms before and after the factorization. And we wind up with just really one level, in terms of our ULV factorization, after we do all the extend adds to merge all the blocks one at a time. Okay? Now we're going to move to the solution stage. So this is all fairly clear so far. So the solution stage, it's the same idea. We again think in terms of we have the same original tree. We think about our switching level, and we do things above the switching level, all in terms of HSS operations, and we do things below the switching level in terms of dense numerical linear algebra. So the first step is that we partition our matrix into BI pieces according to the sizes of the leaf, in terms of the separators at the leaf level. Kind of an analog to how we started our construction, not construction, I'm sorry, our factorization algorithm. Then we start from, now we start at the root. Now the factorization was bottom up, and now the solution stage goes top down. And again, this is similar to LU. We just solve lower and upper triangular systems. We have that other matrix in there, the ULV for stability, but it's the same basic idea. We're solving triangular systems that have now, several of them are structured, and we can do that in linear time to get our solution. So for every node, we solve a triangular system, and then for its descendants, we have to update. You have to, based on the solution calculation you did, you have to perturb's the wrong word, but you have to make a modification to any node below it to account for what you did. That's called updating. It's really the direct analog of a Schur complement. But yeah, and you only have to do this below, and that saves us computationally log n. And that's how you implement it. Okay, so that's what we do with the higher levels. Does that make sense? So it's the same as LU solve, except for we also have to do these updates for the lower matrices. And then down at the bottom, we just use ULV forward substitution. And the fast update can all be done in terms of reduced matrices. This is more direct because we're below the switching level.
I have a question. So,
yes.
When you describe the ULV factorization, you do not use nested dissection, or you use nested dissection and then you apply ULV to the Schur only.
Yes. The first stage of all of this is nested dissection.
So you still do nested dissection.
Yes.
And then you apply HSS ULV to each level's Schur complement.
Yes, exactly.
And you're describing with the solution step with respect to the
dissected, factorized
HSS ULV.
Yes.
Right?
Yes.
So you already have the ULV factorization with Schur at the top level Schur.
Mm-hmm.
You solve for the right hand side B.
Yes.
And then you use to purify the B's of the each independent level right hand side. Then you go there to.
That is exactly what we did. That's actually clearer than I said it. So thank you. Yeah. And so then the final step. So again, to summarize what we've done, is that before the switching level, we've been computing exact solutions just using dense numerical linear, well, it's dense, but it's just basic back substitution, forward substitution. And then after the switching level, we again compute that part of the solution vector through structured computations. And then the final step is just, we put it together. You're traversing the tree for every node and separator from I to going up to the root, using our post ordering, and that gives us our entire solution. Okay. Okay. So yeah, I'm going to make some concluding remarks. This time I'll pause for questions. There's a lot of detail that's swept under the rug, and so I know it's not clear. There's some very good papers by John Linjia and Shiv Kumar, Chandrasekhar, and I think give a very good treatment of this, kind of more step-by-step into some of the details that you need to really get at what's going on. And they have their MATLAB code available online. I think it really helps with this stuff to look at, like MATLAB, it's not industrial, it's not optimized. But if you look at the MATLAB code of this, it's only a few hundred lines, and it really shows you step-by-step what's going on. So kind of some concluding remarks. These are crap. Okay, this is taken from the wrong paper. These results are about 6 years old, but they still give the heart of what I'm going to talk about. So under construction, you see n squared. And so this paper was from before randomized sampling, back when construction was the bottleneck, and it was n squared. In a more recent paper, this would be on.
Which line?
This column. The construction.
This column, so n.
Should, yeah, if you were to do, well, it'd be n log n.
Okay.
If you did it with randomized sampling. Without randomized sampling, that step is n squared. But factorization in the solution, which is what I talked about today, even without randomized sampling, those parts are all linear complexity, even for 3D problems. So, and the memory, no matter how you do it, is n log n at the worst. If you use randomized sampling, it's n. Yeah?
I'm curious how big the constants are in these big O expressions, if they're expected to be pretty big, or if they're actually kind of small. Or?
They're usually, in most algorithms I've worked on, a little under 1,000.
Okay.
So I mean, and which
the size n that you would actually be using these algorithms for, it's not 1,000. I mean, it's not small, but it's not bad.
Yeah.
2 billion a year,
Oh yeah. And that's basically what we reasonably expect. So that's what I was saying. If you have any matrix 10,000 or smaller, I strongly recommend you use GMRes or just a standard nested dissection. You get to bigger and bigger matrices, you have a low rank property. This linear complexity really starts to kick in and give faster results. And so next week, I'll be concluding my series by talking about HSS eigenvalue solvers, which is what I personally do research on. So I think I'll be able to answer questions a little better with that. But I appreciate your time. Thanks, guys.